So we can solve curved beam problems using the Winkler's approach. And Winkler's approach is a strength of materials approach that simplifies the problem. Although you're going to see some of the steps look a lot more involved. So what you see here is a reminder of what's going on here. So you have a curved beam under a moment applied, axial load applied, and shear load applied. So these loads are applied on this surface. And what you have here is a radius, and also you have theta that goes from this axis all the way up. The cross section can be any shape you want. It doesn't have to be symmetric. Later on, I'll show you formulas that are already provided in books that give you a lot of information on how to deal with this. The question becomes is, how can I solve this without having to use area stress function, which requires you to come up with the area stress function is in the first place? We know it satisfies the biharmonic equation, but how you do that in a successful way? So an alternative approach to solving for stresses in a curved beam in Winkler's theory okay, so we have the centroid of the curved beam, the centroidal axis of the curved beam, and then we have the neutral axis of the curved beam, which is right here. And what is a neutral axis? Neutral axis is a location in the radial direction where when moments are applied, there's no stress along that neutral axis. In one of the exam problems I gave you, the principal stress was actually 0 because the location I gave you of that beam was at the neutral axis. The stresses were 0, 0, 0. So the principal stresses are 0, 0, 0. No calculations required. I asked a question to see if you could do it quick. In this case, you can see that the neutral axis may not be coincidental with the centroidal axis. Centroidal axis is a geometric property, while neutral axis is more of a property related to the fact that at that location, no hoop stresses may not be working along that neutral axis. The distance from the curvature or the center point to the centroidal axis is R. We're using R for that, big R. The distance from the center to the neutral axis is Rn. And then we're always measuring positive y-axis going outwards. In this case, R sub naught is the distance to the inner fiber, and then Ri is to the inner fiber, and Ro is to the outside fiber. I also use A for inner surface and B for outer radius surface. So A and B, or Ri and Ro. Okay, so we got that. We're going to use no axial force for the following derivations. Winkler assumed that, what he assumed is that the beam is subjected to moment loads, that this plane stays planar, so it doesn't come out of the page, it stays planar, and that the neutral axis and centroidal axes don't have to be coincident. It's also assumed that the strain distribution through the thickness is linear. So that's an assumption that's also made in this theory. So let's look at what is going on here. So when I look at this point here, what I see is that at this particular point, there's no hoop. So this is what I'm drawing for you, okay? Look at this, what I'm drawing. I'm drawing this line here, APB. That line is this one, APB. That's the line I'm drawing, okay? So this line right here. P is a random location through a thickness, R. And then A corresponds to the inner surface and B corresponds to the outer surface. The thing I want you to pay attention is very similar to mechanics of materials. At the neutral axis, there's no movement of the hoop stress. There's no strain in the neutral axis. You can see here is 0 right there. But any additional rotation caused by the loading applied causes this point to move to the left. This point moves to the right. So you know that this distance from P to this point in the neutral axis must be Rn minus R, because if from the center point to the neutral axis is Rn, and from the point here to P is R, then this distance has to be Rn minus R. So this distance Rn minus R, and this moves an amount phi, delta phi. This moves an amount delta phi has to be, because I told you that that cross section is going to stay planar and is going to just move. So this very similar to mechanics of materials, where you learned that already, that the neutral axis sees no movement, but fibers above it can move left and right linearly respect to the middle surface, the neutral axis. For that reason, we can calculate what the hoop strain is at any point along AB. That formula is given by the following. So I have the initial length. What is the initial length of this? So it goes from here to here. So if I'm looking at P, location P, that length is R times delta theta. Has to be. The length from here to here is R times delta theta. That's just pure geometry. So that's the bottom here. And then this length here, the change in length is given by here, this distance here. And that distance there is Rn minus R times delta phi for small approximation angle approximation. I invite you to check that at home, and I think you will see that that is the case. If I define delta phi divided by delta theta to be omega, and I plug that in, the formula looks a little more simpler. All it's saying is that the hoop strain is going to be omega Rn divided by R minus 1, where R is just a radial coordinate at any point through the thickness. I'll wait there for a couple minutes for it to sink. So if you're wondering what is it, why the delta L is that, right? You can check it yourself, but you get tangent of delta phi, delta L divided by Rn minus R, because that's this edge divided by that edge. But this is approximately equal to delta phi. So I can solve for delta L and I get this. Does that make sense? Why delta L is that much? Okay. So Winkler, what he thought what he was going to do next is, okay, I know strain, so I can calculate stress using this simple formula. He used a simplified version of stress equals strain in this manner. So stress equals the modulus times strain. You know that is not the case for very complex problem. In 3D, it looks very different. We covered that. The moment calculation is written by this formula. So the moment can be calculated with that formula, and is done with respect to the neutral axis, Rn. So what he did next, they plug this hoop stress into this formula here, and then they got this more complicated formula here, which when you expand, you get this formula here. Again, I'm not going to have you memorize this derivation, but I want you to understand where it came from. So basically, first, calculate a strain using pure geometry. That's what Winkler did, just using pure geometry. You can see it's very pure geometry. I didn't do anything fancy. It looks fancy, but it's not. It's changing length divided by original length. Original length is known as R times delta theta. And then he assumed this moves among delta theta, phi. And that's just pure geometry to figure what the change in length is. That's all it happened there. Then the stress is just the modulus times the strain, which is this formula right here. I know epsilon theta theta from this equation, plug it in to get sigma theta theta. And now I can calculate moment. And then once I know moment, I can plug in the hoop strain stress here. You can see that there. Multiply everything out. And when you do, you get this formula. If you notice very clearly, this is a centroidal axis. That's what the centroidal axis is. That tells that this is a geometric quantity that you should be able to calculate. That location, that's giving you this right here. That's centroidal axis. So that's easy. That's R bar. And that's giving a lot of books for different geometries. This right here is area, cross-section area, because integral of dA is area. Done. This is the only thing new that needs to be defined. They call it in books AM, A sub M. You will see that. I did it here. Actually, I switched topics at this point. So just hold this thought for a second. I'll come back to this. Let's look at the sum of forces at this edge. So sum of forces at this edge, we're saying that I'm not going to have any n. So no resultant force n is 0. That's what we're assuming this theory. For that reason, sigma theta theta dA, the integral of that has to be 0. The resultant force on that surface has to be 0. So what I can do, I can plug in sigma theta theta in terms of the formula I had for strain, which is E omega Rn divided by R minus 1. That's what you see there. E is the modulus of the material is not dependent on the area, and neither is omega, the angle change. It doesn't depend on area. So I can write it this way, write the integral nicely as you see here. And this is cool. The n is 0. We said there's no axial force applied. So therefore, this is equal to 0. E omega cancels out. And it turns out I can solve for Rn. I can solve for Rn. And Rn is this formula right here. And that's the neutral that's where the neutral axis occurs. And the formula for Rn is A integral dA over R. That's the formula. Now, good news, this is giving a lot of books for a lot of different geometries. You don't have to do it yourself. Although it would be nice if you learn how to do it. But Rn is, again, let me show you where that is here so you don't forget. Rn is the distance from the center of curvature to the neutral axis. And what is the neutral axis? That's the axis where no Hooke stresses are acting. There's nothing going on there. In the absence of axial forces, just moment. If you apply moment, that's the location of neutral axis. So the cool news is now I know Rn. And I can calculate the centroid distance, which is E equals R minus Rn. So remember the centroidal radius, the radius from the center of curvature to the centroidal axis is R, and the location from the center of curvature to the neutral axis is Rn, and we call this E. That's what a lot of books call it. Returning back to the moment equation that I had earlier, which I actually kind of covered, but I want to come back to this equation. This is AM, recall. I called that AM earlier. And I call, this is A. This is R. That's the centroidal axis. We already covered that. Good. You also realize that and then you can see here from this formula that Rn times AM equals A. You can see here that have Rn squared times AM. Well, that's Rn times AM, and this is A. So I'm looking at this right here. That's this. You can see that Rn times A cancels with one of these two Rn times A. Cancels with one of them. When you do the whole calculation, you get the moment actually simplifies to something very simple. Is E omega A, the cross-sectional area, times the centroidal distance to the neutral axis. Again, I'm not asking you to memorize all these derivations. I'm giving them to you so you're aware how they're derived. Because obviously you're not Winkler. He probably got thesis out of this or a paper journal publication. Actually, it is a journal publication. I'm not going to make you do that in a final exam, but you should at least understand how the theory was developed. And I had to learn it myself. Okay. So if I know, so one thing I know, so we know what the Hooke stress is. We know what the Hooke stress is. We know the moment is. So I know the hoop stress is this. I know the moment is this. But what you could do is you could divide this equation, equation 1 and equation 2, in this way. Because if I divide those two equations, I get rid of E omega, and I get this simple equation now that does not depend on modulus, and it does not depend on omega, which was kind of painful because remember you had this delta phi earlier and this delta theta? I don't have to worry about that anymore because omega was delta phi divided by delta theta. I don't need to know what that is anymore. All I need is the moment that's applied on that curved beam, this moment. All I need to know is where R, the centroidal axis is, R, the neutral axis. That's all I need. And the area, cross-section area. With that information alone, I should be able to tell you what the hoop stress is, the maximum hoop stress is on this system, as a function of R. And you can see very clearly that when I set R equals Rn, what should I get for R equals Rn? Why? Why is this hoop stress 0 at R equals Rn? You. Thank you very much. 20 points for you. So you're correct. The neutral axis is coincident with the location where hoop stresses are not acting on it. And this matches that formula. If you wanted to apply axial load, all you have to do is add an extra term to get the hoop stress completely by superposition. Here, what I show you is different formulas that people came up with. For rectangle, Rn is given here. For a circle is given here, Rn. And R bar here is my big R that I was using earlier. So some books use R bar. I use uppercase R. You can see here for an ellipse is different formula. The cross-section area is also given to you, so you don't have to memorize it. For triangle, it looks like this. And for a trapezoid, it looks like this. And then you can actually do more complicated geometries by combining these geometries. So if the cross-section is made up by one or more of these geometries, you can do that by using summation of areas and things like that, which you should have learned in an earlier class, how to deal with centroidal axis and all that. Okay, any questions on how this works? So